Today I'm going to talk about Chebychevs theorem. This applies to any data set regardless of the distribution shape. This is important because there's a rule called the empirical rule, which applies only to distribution shapes that are bell-shaped. So this actually applies to any particular shape, including bell-shaped. What does this theorem do? It actually aids in interpreting your standard deviation of your data set. Here's what the theorem says. The proportion of any data set lying within k standard deviations of the mean is always at least 1 minus 1 over k squared, where k is any positive number greater than 1. So for this example, what we're going to do is basically pick a couple values of k, plug it into this statement, and see what it means in terms of this example. So here's my example. It says phone calls have a mean of 3.2 minutes and a standard deviation of 0.6 minutes. Draw conclusions using Chebychevs theorem. So again, what I'm going to do is just start picking values of k, plug into the formula, and then interpret what that means in terms of this phone call problem. So notice if I go back up here, it says k is any positive number greater than 1. I'm going to start out with the obvious. Let's let k equal 2. So if I let k equal 2, my next step is going to be to plug into this, because remember, this is going to tell me the proportion. So if I let k equal 2, that's going to be 1 over 1 minus 2 squared. What is 2 squared? That's a 4. So we now have 1 minus 1/4. And so that gives us 3/4. Or a lot of times it's easier to understand proportions in terms of percents. Hopefully we all agree that's the same thing as 75%. So if I come back to this interpretation, what does this mean? It means that 75% of the data set of phone calls, right, because that's what this particular example is about. So 75% of the data set of phone calls lies within k standard deviations of the mean. So phone calls lies within k in this case, right, was 2. So within 2 standard deviations of the mean. So in this case, I can actually provide a little more information to help that make sense. I know that my mean is 3.2 and my standard deviations is 0.6. So if I were to take the 3.2 here in the center and add 0.6 and add 0.6, right, to get 2 standard deviations, and similarly subtract 0.6 and subtract 0.6, within 2 standard deviations of the mean in this example is anywhere from 2 to 4.4 minutes. So again, 75% of the data set of phone calls lies within 2 standard deviations of the mean, or 75% of the data set of phone calls lies between 2 and 4.4 minutes. Just as a second illustration to really hopefully make this hit home, let's try it again with k equal to 3, right? Again, k just has to be any positive number greater than 1. We already did 2, so let's try 3 this time. So again, I'm going to go back to my formula. So in this case, 1 minus 1 over 3 squared. So 1 minus 1/9. That equals 8/9, or again, if I want to turn that into a percentage, which is usually easier to understand, that's about 89%. So again, plugging it into this generic statement, I'm now going to have 89% of the data set of phone calls lies within So I have lies within 3 standard deviations of the mean. And again, if I wanted to, I could come back out here, add another 0.6, subtract another 0.6, and those two values are between 1.4 and 5 minutes. So again, 89% of the data set of phone calls lies within 3 standard deviations of the mean, or 89% of the data set of phone calls lies between 1.4 and 5 minutes. So 2 examples here of Chebychevs theorem applied to this example about phone calls.